Hey there, science fans! Today we're diving into the fascinating world of number systems. You might be thinking, number systems? What's so exciting about that? Well, get this. Computers, those amazing machines that power our digital world, don't speak our language. They use a special language called binary to store and process information. You see, computers are like giant collections of tiny switches. These switches can be either on or off, just like a light switch. In computer language, on is represented by a 1, and off is represented by a 0. That's binary, just two numbers. It's like a secret code that computers use to communicate. But don't worry, you don't need to be a secret agent to understand binary. Once you get the hang of it, it's actually pretty simple. And besides binary, we'll also explore decimal, the number system we use every day, and hexadecimal, another important system used in computer science. So, put on your thinking caps and get ready to learn the language of computers. Let's start by learning how to convert a decimal number, like the number 77, into its binary equivalent. This process might seem a bit tricky at first, but once you get the hang of it, it's like decoding a secret message. Imagine you have 77 cookies. Yum! You want to share this information with a friend who only understands binary, which uses only ones and zeros. To do this, you need to convert the number of cookies into binary. Binary is a base 2 number system, which means it only uses two digits, 1 and 0. This is the language that computers understand. Here's how to do it. First, find the largest power of 2 that is less than or equal to 77. This step is crucial because it helps us break down the number into manageable parts. The largest power of 2 less than 77 is 64. This is because 2 to the power of 6 equals 64. So, we write down a 1 because we are using that 64. This one represents 64 in binary. Next, we subtract 64 from 77, which leaves us with 13. This subtraction helps us figure out what remains to be converted. Now, we look for the next largest power of 2 that is less than or equal to 13. The next power of 2 is 32, but 32 is too big for 13. So, we write down a 0, because we skipped 32. This 0 indicates that 32 is not part of our binary representation. We continue this process, moving to the next lower power of 2 each time. The next power of 2 is 16, but 16 is also too big for 13. So, we write down another 0. This 0 shows that 16 is not included in our binary number. The next power of 2 is 8, which fits into 13. So we write down a 1 and subtract 8 from 13, leaving us with 5. Now we look at the next power of 2, which is 4. 4 fits into 5, so we write down another 1 and subtract 4 from 5, leaving us with 1. The next power of 2 is 2, but 2 is too big for 1. So we write down a 0. Finally, we have 1 left, which fits perfectly, so we write down a 1. Now, we have our binary number. String those 1s and 0s together, starting with the biggest place value. The binary representation of 77 is 1001101. Congratulations, you've just decoded a secret message. This binary number can now be used in computer systems to represent the decimal number 77. Understanding binary is a fundamental skill in computer science and helps us communicate with machines. Keep practicing, and soon you'll be a binary conversion expert. Now that we know how to go from decimal to binary, let's reverse the process. This is an essential skill in computer science and digital electronics, as it allows us to understand how computers interpret and process data. By mastering this, we can better appreciate the inner workings of the technology we use every day. Say we have the binary number 1001101, and we want to know what it represents in our familiar decimal system. This binary number might look like a random sequence of 1s and 0s, but it actually holds a specific value that we can decode. Remember how we used powers of 2 in the previous section? This method is fundamental because binary is a base 2 system, meaning each digit represents an increasing power of 2, starting from the rightmost digit. We'll do the same thing here, but in reverse. Instead of converting from decimal to binary, we'll convert from binary to decimal by applying the same principles. Write down the powers of 2, starting from the rightmost digit of our binary number, 1, 2, 4, 8, 16, 32, 64. These powers of 2 are the building blocks of our binary number. Now, multiply each binary digit, 0 or 1, by its corresponding power of 2. This step is crucial because it helps us determine the value each binary digit contributes to the overall number. If the digit is 0, the result is 0. This means that particular power of 2 does not contribute to the final sum. If the digit is 1, the result is the power of 2 itself. This indicates that the power of 2 is included in the final sum. In our example, we get 1 times 64, plus 0 times 32, plus 0 times 16, plus 1 times 8, plus 1 times 4, plus 0 times 2, plus 1 times 1. Each of these products represents a part of the final decimal number. Add up all the results and voila! This step brings together all the individual contributions of the binary digits to form the final decimal number. We get 64 plus 0 plus 0 plus 8 plus 4 plus 0 plus 1 equals 77. This final sum is the decimal representation of our original binary number. We've successfully cracked the binary code and converted it back to decimal. This process not only helps us understand binary numbers but also enhances our problem-solving skills and logical thinking. Keep practicing, and soon you'll be a pro at converting between binary and decimal systems. Section 4. Binary to hexadecimal, a shortcut for long codes. Today we are diving into a fascinating topic that can make your coding life a lot easier. Dealing with long strings of ones and zeros can get tedious. Imagine having to write out or read a long binary sequence every time you work on a project. It can be overwhelming and prone to errors. That's where hexadecimal comes in handy. Hexadecimal, often referred to as hex, is a more compact and human-friendly way to represent binary data. Hexadecimal, or hex for short, uses 16 different digits, 0 to 9 and A to F. This means that each hex digit can represent a much larger range of values compared to a single binary digit. Each hex digit represents a group of 4 binary digits or bits. This grouping makes it easier to convert between binary and hexadecimal. To convert binary to hex, we simply group the binary digits into sets of 4, starting from the rightmost digit. This systematic approach ensures that we don't miss any bits and makes the conversion process straightforward. If the leftmost group has fewer than 4 digits, we add zeros to the left to make a complete group. This padding with zeros ensures that each group is a full set of 4 bits, which is necessary for accurate conversion. Let's try it with our trusty binary number 1001101. This example will help us see the conversion process in action. Grouping it into sets of 4, we get 01001101. Notice how we systematically group the digits to ensure accuracy. Notice how we added a 0 to the leftmost group. This padding is crucial for maintaining the integrity of the conversion process. Now we convert each group of 4 bits into its corresponding hex digit. This step is where the magic happens, transforming our binary groups into more manageable hex digits. 0100 is equal to 4 in hex, and 1101 is equal to D in hex. By understanding the value of each group, we can easily map them to their hex equivalents. Therefore, the hexadecimal representation of 1001101 is 4D. This conversion shows how a long binary number can be represented in a much shorter and more readable form. See how much shorter and easier that is to work with. Hexadecimal not only saves space but also reduces the likelihood of errors when reading or writing long binary sequences. Hexadecimal is like a shorthand for binary, making it easier for us humans to read and write long binary numbers. This shorthand is especially useful in fields like computer science and electronics, where binary data is prevalent. By mastering the conversion between binary and hexadecimal, you can streamline your work and improve your efficiency. Practice makes perfect, so keep working on these conversions to become more comfortable with the process. Understanding and using hexadecimal can significantly enhance your ability to work with binary data. It's a valuable skill that will serve you well in many technical fields. So next time you encounter a long binary number, remember the power of hexadecimal. It's a simple yet powerful tool that can make your coding tasks much more manageable. That's it for today's lesson on binary to hexadecimal conversion. Keep practicing, and soon you'll find that working with long codes is no longer a daunting task. Happy coding! Section 5. 2's complement. Negative numbers in binary. So far we've only talked about positive numbers. But what about negative numbers? How do computers represent those in binary? That's where 2's complement comes in. It's a clever system that allows computers to represent both positive and negative numbers using a fixed number of bits. In 2's complement, the leftmost bit of a binary number represents the sign. If it's 0, the number is positive. If it's 1, the number is negative. To find the 2's complement of a binary number, we follow these simple steps. 1. Invert all the bits. Change zeros to ones and ones to zeros. 2. add 1 to the result. That's it. Let's try an example. What's the 2's complement of 00101101, which is 45 in decimal? 1, inverting the bits, we get 11010010. 2, adding 1 we get 11010011. Therefore 11010011 represents negative 45 in 2's complement representation.